Konrad Lehnert, JILA. Okay, good. Hi, thanks so much for the invitation to speak at this workshop. Today I'm going to describe opportunities to deploy emerging tools in quantum measurement and control in some kind of fundamental physics experiment. I'm really thinking about, in this case, the sort of superconducting circuits associated with the quantum information science program. That's sort of my domain of expertise. And I'll tell you a story about using those in particular in the search for an ultralight dark matter candidate called an Axion. I'll tell you really mostly about kind of work that takes place in my lab, but I'm also part of a legitimate Axion dark matter search. In the sort of high energy physics collaboration sense, we have a name, and we're a collaboration of two groups at Yale, a group in Berkeley, and my group in JILA. In spite of the storied tradition of laboratory astrophysics, JILA no longer acknowledges that the LA stand for laboratory astrophysics. Right. Well, I have the wireless presenter if you're not going to use it. So in outline, what I'm going to tell you about today, or the perspective I'm going to promote, is that we should think of these searches for ultralight dark matter as a kind of quantum metrology problem. I'm going to end up giving a kind of parallel, very similar talk to Mark's talk in this sense. I'm going to argue that that's sort of a useful perspective, that it gives useful insights in how to think about extending the reach of those kinds of experiments. And I'll show you that the axionic dark matter search really can benefit from this emerging quantum circuit technology. And in particular, quantum squeezing is being deployed today to accelerate a dark matter search. So everything that I know about dark matter fits onto one slide. Fortunately, I think if you're severe enough about the word no, maybe most of what all of us know about dark matter fits onto one slide. At least we think that it is cold in the sense that it is essentially gravitationally bound to luminous matter, and therefore to us, it has a mean density in the sort of few tenths of a GeV per cubic centimeter, and it must be weakly interacting, otherwise we would have already detected it in our laboratories.
Or it could be non-interacting except for gravity.
It could just be gravity. So weak includes zero. This is, let's see, semi-definite weak. Includes zero. If you posit some kind of fundamental particle origin for dark matter and you say those fundamental particles have a rest mass energy less than about 1 electron volt, then these facts alone really tell you that your dark matter field is a quantum degenerate Bose gas. That, in essence, just the statistical mechanics of those claims mean that for light enough particles, you have phase space density that you're quantum degenerate. And the real implication of that is that it's useful, better really, to think about the dark matter field as being more field-like than particle-like. Rather than detecting a rare scattering off of some heavy lump of stuff, you're looking for a persistent, large amplitude, very weakly coupled field oscillating at something like the Compton frequency of the particle that you're looking for. And so searches for that kind of dark matter, laboratory searches, they have a flavor, many of them, which correspond to building some kind of high Q oscillator or resonator in your lab. Might be a resonant circuit, might be a microwave cavity, ensemble of spins, maybe even a mechanical resonator. Then you simply say that high Q resonator has some kind of coupling to the putative dark matter. That coupling is inevitably weak, but the dark matter field is highly occupied. And so the task of the experimentalist is to distinguish evolution of that laboratory oscillator under some kind of null hypothesis where it's uncoupled, or evolution where it's coupled to some kind of classical force. And classical force, in this sense, simply means that this coupling is so weak that I needn't worry about the decoherence or dephasing of this high Q oscillator due to its coupling to the dark matter field in comparison to all of the mundane stuff that inevitably is going to decohere the oscillator. So in that sense, it really is just a kind of Hamiltonian parameter estimation problem. So since it's a harmonic oscillator, it'll be useful to move into a phase space picture and to think about quadrature amplitudes that evolve at the oscillator's resonance frequency. And in that sense, classically, you can imagine preparing your oscillator at a point in phase space. And in this picture, it'll just stay there unless it's acted on by some force, the thing that you're trying to detect. If you happen to make the oscillator resonant with that dark matter field or with whatever that oscillatory classical force is, it'll simply walk away from the origin, a little bit detuned, and it's just going to execute little circles in phase space. So the task is then prepare the system in as small a volume in phase space as you can, let it evolve for some period of time, and go measure it as precisely as you can, and infer the presence or absence of such a force. Now, clearly, if you do a good enough job of that preparation and measurement, eventually you're going to encounter the fact that these quadrature amplitudes are non-commuting observables. In fact, they're canonically conjugate. We can represent the associated Heisenberg uncertainty principle just by some kind of little blob. And that's clearly going to pollute any inference of such a classical force acting on an oscillator. And if your measurement tools and control is good enough that you can prepare, say, in a quantum ground state, and then later on measure both x and y as well as you're allowed to, localizing the state as much as you're allowed to, then the tradition, awkward as it is to call that operating at the standard quantum limit. We would be happier if we called it the coherent state limit, but alas. And so even though the quantum fluctuations are fundamental, they're of course not unavoidable, you could beat the standard quantum limit by saying, look, let's not measure both of these non-commuting observables, let's just measure one. And in particular, maybe we should first prepare the system in an eigenstate of the thing that we're eventually going to measure. So we could imagine preparing in an eigenstate of this x observable, waiting for some period of time, and then just measuring x. At least for the component of the force that's sort of directed along the x-axis, your measurement is like independent. It's not in any way polluted by that quantum noise. Of course, that's an idealization. An eigenstate of a single quadrature of a harmonic oscillator has infinite energy. States that approach that are these so-called squeeze states, and that's basically an example of quantum metrology, saying, given that you want to detect some parameter in the Hamiltonian, what's the best possible state I might prepare my system in? What's the best possible variable to measure? Now, I haven't said much about decoherence of the oscillator, and indeed, you can understand that if I wait too long, my squeeze state, all that fine structure and phase space that I've prepared is going to be destroyed. If you're in the situation where this classical force that you're trying to detect is taking on new values on some time scale fast compared to the coherence time of your oscillator, well, then great. You needn't worry about it. You're simply going to prepare and measure on some cadence very fast compared to that decoherence time. And that's essentially the situation that's considered in this now rather famous review published some 39 years ago. And you can tell by the authors that they were thinking about the detection of a weak classical force on a quantum mechanical oscillator. That problem for them was really detecting gravitational waves. Indeed, we've known about these quantum metrology possibilities for a long time. This is the year that LIGO is deploying squeezing inside of its search. It is in some sense, hard to beat the standard quantum limit in a fundamental physics search or experiment. I don't have a theorem that that's true, but here's my dumb way of thinking about it. If you want to couple to some fundamental interaction, particle, or field, usually you make a big thing. That's an image of a famous Weber bar. An aluminum resonator of a few tons, the thing over which you have really good quantum measurement and control, like this few micron aluminum resonator, these are just very different scales. In some sense, I think as Mark said very nicely, the benefit of quantum metrology is in reducing some kind of resources required to reach a specified precision. It may well be cheaper just to build a bigger experiment or to build multiple experiments than it is to figure out how you're going to first reach the standard quantum limit for whatever measurement you're doing, let alone beat it. It's also true that you require a kind of technical perfection. It's if you say, look, I can prepare a squeeze state, and then I can measure the squeeze quadrature with a noise only as large as the noise that I would have if I'd measured both quadratures. Well, don't bother squeezing. It really, it's just unhelpful. So you have to be able to really have extremely good control and measurement. And it is generally the case that you win in situations where the resonator coherence is better than the signal coherence. The example I'll describe today is a kind of edge case of that claim. All right. So the problem of microwave frequency Axion dark matter detection, that's a situation where you're really in a situation where you can benefit from these quantum metrology concepts. In particular, there are a whole family of sophisticated tools that allow you to manipulate and measure microwave fields really much better than we could 10 years ago. And it's also the case that that experiment is in a situation where kind of increasing the signal, making the experiment bigger, is really kind of prohibitively expensive. So I will, I guess, describe in this talk really just this part of the story, what you can do using parametric amplifiers that use the Josephson effect. Okay. So the story of axionic dark matter, I'm the wrong kind of physicist to do this much real justice, but it is born out of a hypothesis to resolve the strong CP problem in QCD as a kind of a consequence appreciated later. That hypothesis leads to an associated particle, which is a viable dark matter candidate. There's a strong experimental constraint that says it should have a rest mass energy lighter than about 2 millielectron volts, and there's really no kind of limit on how light it can be, but just to sort of restrain my insanity, I feel comforted by thinking about kind of post-inflationary scenario, such models which would leave this unknown mass in a kind of 3 orders of magnitude range between 2 micro eV and 2 milli eV, expressed as a frequency that corresponds to something like 500 megahertz to 500 gigahertz. So very, very light from a particle physics perspective. The consequence of that hypothesis is that there's an effective coupling of the Axion field to electromagnetism, coupling really to things that look like electric field dotted into magnetic field. The standard laboratory trick is then to linearize around a great big static magnetic field, and then you get resonant conversion of the Axion field to an electric field oscillating at the Compton frequency of that dark matter particle, so long as you're basically at rest with respect to it. And that's going to be some kind of conversion from the Axion field to microwave frequency photons. So the idea, really now going back some 36 years, on how you look for dark matter of that type, due to Pierre Sakivi, is, well, you build a microwave cavity, hopefully resonant with that oscillatory electric field, or at least close to resonant, stick it in the biggest static magnetic field you can afford, and then you measure the field in the cavity. The way you do that is by letting some of the field in the cavity leak out, direct that to the best microwave amplifier you can get your hands on, and current experimental constraints are that the coherence of that cavity is actually quite a bit worse than the putative coherence of the Axion field. Something like a Q of 10,000 for a cavity which has to live in a 9 Tesla magnetic field, whereas something more like Q of 1,000,000 for the inverse line width of that Axion. So you look then over the frequency range of the cavity resonance in something like 100 little independent frequency bins for a bit of excess power poking up above a noise background. And when I say a bit, it's something like a spectral density that corresponds to something like 10 to the minus 3 photons, and operating at the standard quantum limit in sort of radio engineering language, that would correspond to 1 photon of spectral density. So you're looking for a little bit of excess noise power of a part in 10 to the 3 on a 1 photon background. Well, if you average a random process 1,000,000 times, you can determine its variance with a precision of about a part in 10 to the 3. So your cavity is tunable. You tune it to some frequency. You wait, beating down the noise to allow you to resolve things like that. Not finding such a thing, you then tune to an adjacent frequency and do some more waiting. And slowly and painfully, you walk through frequency space looking for this unknown mass and therefore frequency. And that's why it's kind of a very slow process. So this is a sort of a summary of what I think is known from this experimental technique as of sort of April of 2018. I think that's the ADMX result from that time. These are all the haloscope results. And on the x-axis is rest mass of the Axion, or expressed as a frequency on the upper y-axis. And the Axion hypothesis is not a single parameter model, it's a family of models. If you know the mass, you know something about the coupling, which is what's plotted on the y-axis. And roughly speaking, there's a model band, and that's what this yellow region represents. So you can see it's only a tiny fraction of that yellow region that has been probed, and furthermore, this yellow region really represents only a tiny fraction of that 3 orders of magnitude, 3 decades in frequency that you have to search. So, and in particular, it's even a little bit misleading to think of it in this way. whether you want to go down more deeply into weaker couplings or up to higher frequency, in both cases, it's the rate at which you can scan through frequency scales appallingly badly with both of those. It's a very high polynomial. So really, you can say, well, what would it take if I could reach standard quantum limited sensitivity and I would use a 9 Tesla magnet? I would spend just scanning 1 decade, this 1 to 10 gigahertz frequency, 20,000 years. Okay, maybe no one's willing to wait that long. So you can instead upgrade to a 30 Tesla magnet. You can have 16 of those, and then it's 10 years. This is a very crude estimate, $1.2 billion of what maybe such a farm of gigantic magnets and the people to run them would cost. So you are really in a situation where you are very much signal starved. You are dominated by quantum fluctuations. So doing better then, can you implement this simple picture of sort of squeezing in this world? Yes, and in particular the key tool is the so-called Josephson parametric amplifier. This is really nothing but an inductor capacitor resonant circuit where the inductor is variable using the Josephson effect. They were developed, I think just to study them in the, that goes from sort of an era of the 60s to the late 80s, and then it all came back again with superconducting quantum information science. We make things that are pretty close to textbook pictures of these parametric amplifiers. They are quite literally capacitor inductor resonant circuits where we vary the inductance at twice the natural frequency of that LC circuit. That gives you a narrow band parametric amplifier, but one whose narrow amplification band can be tuned around just as you tune the Axion cavity. You have lots of gain to overwhelm the noise of subsequent amplifiers. And to the degree that we can measure it, they don't add noise or introduce fluctuations above the requirements of quantum mechanics. Sure, they do. It's just that there's a precision to which we can measure, and we haven't been able to resolve that. Okay. So what it means for them to operate in a way where they measure just one quadrature is simply to say we pump, that is to say we vary the inductance at a frequency centered on the band of that Axion cavity. You can think of the transformation in phase space performed by that amplifier really as just amplifying one quadrature and squeezing or the orthogonal quadrature. And any information encoded in the X quadrature is then amplified. The noise gets amplified as well, but there's no noise added. Clearly, if you can do that, you can also squeeze. Just by adjusting the phase of the pump field, you can, say, feed vacuum and end up with the X quadrature squeezed. So a pair of such parametric amplifiers can be used, one to prepare a squeeze state and one to later measure it. So you show that pretty well just by putting two of them back to back. First parametric amplifier is used to squeeze vacuum, a second parametric amplifier to do a single quadrature measurement of that squeeze state where you vary the phase of the quadrature you measure relative to the quadrature that you squeezed, and you can just plot a histogram of all the little voltages that you measure as a function of that relative phase and see strong suppression below vacuum fluctuations of about 4.5 dB. No inference, no subtraction in here. This is 2 times square root of 2 reduction in the variance below vacuum fluctuations in the full experiment. That corresponds to a kind of an efficiency of transporting the squeeze state from the output of this amplifier into the input of that one of about 70%. And so how do you deploy that in an Axion search experiment? We have the microwave cavity that couples to the Axion field. Let's make a kind of model for how that couples. In particular, we want to think about the sources of noise and the loss, the ways in which that cavity loses energy will enumerate for us the sources of noise basically through the fluctuation dissipation theorem. The cavity can lose energy by the fact that we are trying to measure the cavity field by removing some of that field and sending it to an amplifier. It can lose energy because it's not perfect. It's got some intrinsic absorption. We can model that with a kind of fictitious transmission line that carries microwave fields away and directs it to some resistor. And then finally, there's the nominal Axion coupling, whose coupling is assumed to be just tiny compared to these loss rates. The hope of detecting something is simply to imagine that the Axion field is kind of like a giant microwave generator, just incredibly weakly coupled to that cavity. And that makes it this weak classical force. So the key insight is really that you can change two things. You can change the cavity's resonance frequency, and you can change how strongly coupled the measurement port is to the cavity. Once you have spent the money on the magnets and made the highest Q cavity you know how, those things are kind of fixed and frozen. What you can adjust in the experiment is resonance frequency of the cavity and how strongly the cavity is coupled to its measurement. No matter what you choose for the resonance frequency of the cavity and for how strongly coupled it is, the fluctuations that come from the intrinsic loss of the cavity at the same frequency as this Axion field, they're processed in exactly the same way. Doesn't matter what frequency, doesn't matter how strongly coupled, they're always proportional to each other. That's a kind of fundamental technical limit to the signal-to-noise ratio in such an experiment. The only thing that you really need to do is just ensure that the noise from this other source, from this measurement port, that is minimized. And in particular, the loss port, well, those represent real physical dissipation of the cavity that you kind of declare that you can't have access to those quantum degrees of freedom by calling it loss. On the other hand, this measurement port, there's a 50 ohm termination that you buy from a microwave supply company that represents that loss. And you can do something about that. So what you do, well, there's two ways to make the noise from this port vanish. One way, as any microwave engineer would tell you, is make the cavity coupling and loss the same, like the kind of loss rates to the absorption and to the outcoupling equal to each other. That's so-called critical coupling. And then at frequencies right on resonance, you'll simply absorb any field that's incident on the cavity, inside the cavity itself. And all the noise at that frequency, at the cavity's resonance frequency, will just come from these fluctuations. That's sort of one strategy. That's sort of resonant signal and critically coupled. And that gives you a bandwidth in your measurement, which is just twice the intrinsic loss rate of the cavity. In contrast, you could imagine coupling to much more strongly to the cavity. That would reduce the field that you want to detect, how much of it reaches the amplifier. It would reduce the noise that comes from this source, how much of that reaches your amplifier, but much more of this measurement port noise would reach the amplifier. No problem. Then you squeeze it. And you have gotten back, in principle, to the same signal-to-noise ratio, but now with substantially more bandwidth. You scan through frequency faster, and that's the win. So if you can squeeze infinitely, then you can really get back to the same signal-to-noise. In reality, what you will trade off is in sensitivity. In the case of no squeezing and critical coupling, a small reduction in the sensitivity for a much greater bandwidth, a much greater range of frequency over which you achieve that. So to the degree that you can overcouple and squeeze, you can accelerate your search. In principle, that's sort of the no loss, no absorption picture. So this is a situation where the putative axion is spectrally narrow compared to the cavity. And indeed, if you, but it's maybe unhelpful to think about it as really looking for a narrowband signal in one sense. Since you don't know its frequency, it really acts much more like a spectrally broad situation where if I were to say my prior knowledge of where I expect the kind of axion power to be is actually very, very broad, then it's clear why squeezing helps. And in fact, if I knew the rest mass of the axion, if some astrophysical signal told me what frequency to go look for, no point in even turning on the squeezer. You would tune the cavity into resonance, you would critically couple, but you don't, or at least I don't. And so consequently, you have what acts like a kind of broadband search. All right. So is doubling, with an efficiency of 70%, you cannot deliver arbitrarily good squeezing to your cavity, and your measurement isn't perfect. And that means that in the end, you get an increase in scan rate just a little bit more than a factor of 2. Is that any good? It would save you 10,000 years or $600 million. Maybe another way to say it is, look, this is a factor of 2 or so innovation. You would need a few similar innovations that don't interfere with each other, and suddenly 2 to the 6th power or so is a biggish number. And or maybe the last point I like to make is just you now have something to work on. You get dramatic improvement in how well you can do as you make the loss in transporting a signal from one of these parametric amplifiers to the other. And if you were stuck at the quantum limit, well, there would be nothing to work on. You would simply, have to deal with these kind of things. Maybe a little in the spirit of what Mark said, I think we felt like in order to really demonstrate that this worked, rather than just sort of showing that you could create and analyze a squeeze state, we wanted to really recover a signal and to demonstrate that we got the speed up as promised. And so we did that by building a kind of physical instantiation of that Axion search model, where it's now a superconducting cavity, and we introduce intentionally loss that models the lossy Axion cavity, and then our Axion field is actually sourced by a microwave generator that is very, very weakly coupled to that cavity. So 3 ports coupled to that aluminum box, one being the measurement, one being the kind of something to intentionally introduce loss, and then something to very weakly couple in a microwave field. And we can vary this kind of measurement port coupling between critical coupling and something like 10 times overcoupled. So just to show you the squeezing really does what we say, if we put in a microwave tone off resonance, it comes through to our measurement in the absence of squeezing. It pokes up above a noise, turn on the squeezer, and that noise floor drops by 4.5 dB. If we compare to critical coupling, the signal-to-noise ratio as a function of Fourier frequency, we can see the Lorentzian line shape of the cavity in that signal-to-noise ratio. Rather than critical coupling and not squeezing, we can overcouple. You lose sensitivity on resonance, gain bandwidth, and the net effect of this is that you still lose because on this logarithmic scale, this really hurts a lot. But turn the squeezer on, win back most of that sensitivity, and then this really corresponds now to a scan rate for searching for a signal or frequency you don't know to that full factor of 2. And that's described in much more detail in this paper we published this year. I can tell you that we've taken that apparatus out of our lab. We've sent it to Yale, where the actual Axion search experiment lives, installed it in a new dilution refrigerator, done the full commissioning and testing, and the haystack science run is in progress now. And yes, we turned on the squeezer, and yes, we get the full 4 dB reduction in noise. So I can say that a squeeze state receiver is being used today in the search for dark matter. Let's see, I have 3 conclusions on here that are relevant, and then a 4th one, which was based on some naive ambition about how much I was going to cover in a 35-minute talk. I'll take any questions.
So you said that the squeezing is limited by 69% efficiency, and there's plenty to work on there. Can you elaborate on that? Is there any hope of getting better than that?
Yeah, definitely. So how do you do better? Maybe if anyone who's kind of spent time in this world will probably understand that this little microwave symbol here with the arrow going around in a circle, the circulator, it's one of the kind of problems. And in particular, in our experiments, these are commercially sourced ferrite circulators. They're not especially intended to be the very lowest loss they might be. Even if they were perfect, though, you're doing a terrible thing. It's wonderful because adding an element like this really makes this a cascaded system. You never need to think about fields leaving the cavity and going back to the squeezer. But that also means that any kind of reflection of the microwaves after the circulator that reflection is then going to be a kind of loss, because the circulator is going to do what you ask it to do, which is to prevent that field from going back. It's going to direct that to some 50 ohm resistor. So the way to do better is really to get rid of these circulators. There's different ways you can do that, and different ways you can think about that. One way that I hinted at was using kind of lossless superconducting switches. Maybe a different and possibly better idea is just to stop thinking about really working with cascaded systems. You can do all this kind of two-mode squeezing, you can do all the squeezing physics, but in a system where you don't imagine preparing it in one location, transporting it, and measuring it in another location. I think that's probably the way that we'll win.
Could you say something more about measuring both quadratures noiselessly?
Only very briefly, because I'm not as prepared as I should be, but I did actually, let's see, I thought I would be crafty and try to do that. Okay. So can you measure both quadratures of the cavity field without noise? No, not as long as quantum mechanics is the correct theory of nature. Can you measure both quadratures of the Axion field noiselessly? To the degree that it acts like a classical force, sure. It's entering your Hamiltonian as two commuting numbers, and you just want to estimate two numbers rather than one number. How do you do that? Well, one strategy is you have two cavities. One is really just going to be a kind of dummy cavity, and you form EPR-like observables Q and P, which commute with each other. There are linear combinations of the two cavities, and eigenstates of these Q and P operators are like the sort of two-mode equivalent of the single-mode squeeze state. And you can make something like that using two-mode parametric amplifiers, which are used extensively already in our field. So a receiver that would measure both quadratures would really be something where you started with two vacuum modes. You would prepare them into two-mode squeeze state, inject those into two cavities, only one of which is coupled to the Axion field. That gets displaced, you then kind of undo the two-mode squeezing operation that brings you back to vacuum, except for this little uncorrelated bit, which is the force you wanted to measure, which now gets amplified and appears at the output of both of these sort of signal annihilator ports. It's as if you have amplified the Axion signal and not the noise. Sort of a...
The Axion signal in one cavity.
Pardon?
How do you turn off the Axion signal in one of two? So
Oh, that's quite simple. You just have one of the cavities not in a magnetic field. So the Axion coupling is proportional to the magnetic field strength. That's right. If you couple to both and you were clever about it, it would be like building two experiments, but you would win from doing that. Oh, sorry. Go ahead, David. Sorry, we're sorry.
So, I mean, this is really nice stuff and helps you with the kind of bandwidth problem. But if we're a bit unlucky in the Axion photon coupling for the QCD Axion, you still also have a sensitivity problem in ASTEP, right?
Oh.
So, I mean, other than bigger magnets and better cavities, is there any quantum measurement technique that can help you go down faster?
Well, I think ultimately, this sort of, yeah, good. So you could, perhaps you're inviting me to answer, had I remembered how to put the little return arrow, I would have done that. You can imagine counting photons instead of measuring fields. And I don't know if that goes down in the sensitivity sense. Really what photon counting is, it's a kind of background-free measurement. Your cavity, the fact that it's cooled in a dilution refrigerator, it's kind of preparing it in an energy eigenstate, and then you're measuring an observable, which commutes with the Hamiltonian. And in that sense, you can measure number. And if you can really do that in a background-free way, where there's really no thermal photons around and your photon counters are perfect, then yes, you can win really quite a bit faster. It's a situation where you win to the degree that you go lower in physical temperature and higher in frequency. At the moment, for the 5 gigahertz range and kind of looking at the experiments in detail, I think it's probably still a better route to go with squeezing. Once you get above about 10 to 15 gigahertz, for sure you want to be photon counting. Can you photon count in the microwave domain? Thanks to superconducting qubits, yes. Can you photon count with really, really low dark counts? Yes. You can do QND measurements of photon number, which means you can have a detector which you get several chances to detect the same photon. So even if it lies every once in a while, you can do a kind of majority vote.
Another thing you might be able to do with two cavities are very different. But of course, the cavity is a microwave receiving antenna, and any receiving antenna can be a transmitting antenna. Microwaves into it. So you can have one cavity in lots of microwaves into it. You do the inverse, the Primakov conversion of axions, and generate your own axions.
I'm aware of the possibility of these things, and there are, of course, active experiments, that, to my knowledge, that try to do things like this. They, of course, are harder in the sense that you both have to suffer the feeble axion photon coupling both in the creation and in the detection. And I assume that these become a sort of challenge of having an enormous amount of power in one place and an incredibly sensitive detector nearby, and discovering just how many dB of isolation microwave connector really has. I don't have much personal experience with these kinds of experiments. I'm aware of their existence. As a kind of person who is the amplifier friend to a dark matter search, I will say that the sorts of things that I know how to do maybe are not super relevant to I don't know, having a kilowatt or more of microwave power in a cavity. There are people who know how to do that. It's not my kind of guy.
Are there, so you described a beautiful set of science experiments that can exploit the noise control you have with parametric. Are there technologies that also benefit?
Well, do you consider quantum information, science, as in computing, a technology?
Like sometimes you hear people talk about quote quantum radar.
Yeah. Okay.
Which I think
quantum
is maybe not an interesting technology, but is there something like that?
So, when you think about these things, in order to kind of benefit, you really want to be in a situation where at microwave frequencies, you have your source itself is quiet. So this is things where the signal is sort of itself generated inside of a dilution refrigerator. So in terms of a big commercial technology today, there's not that many people who generate microwave signals inside of dilution refrigerators. If there are, I can for sure, give them or sell them something that will measure that better. But that has tended to be either some kind of precision measurement science customer or a kind of quantum computing, quantum information. I don't know of other kind of maybe you could imagine something like a magnetic resonance experiment where you would benefit from techniques like this.
What about the Deep Space Tracking Network, who already use parametric amplifiers in their front ends?
So let's see. I'm profoundly ignorant of whatever it is that you're telling me, but I'm going to, I'm come equipped with a Y chromosome, so I'm going to answer that question. So to the degree that you're working at microwave frequencies in the few gigahertz range, space is in some sense hot at those frequencies, and so it's possible using the amplifier that follows our parametric amplifier, something that we used to get from radio astronomers, now get from a company that makes these things commercially for people like me. It operates basically at kind of pretty close to that thermal background limit for a few gigahertz. You really has to be a situation where the source itself there's sort of a very low background, and I think so. I don't know what frequency the Deep Space Tracking Network works or what parametric amplifier technology they're using, but I would be surprised that I could easily kind of plug into what they do.
Nice way to end this discussion.